I've been asked to do more programming type videos rather than the mathematical operation videos I tend to do. This video goes over an example of loops, conditional statements, and procedures. It is based on a viewer request on the Collatz Conjecture. Let's get started. So this particular example is based again on a user request. This is about the Collatz Conjecture, which you can read on Wikipedia. Basically, the conjecture asks whether repeating two simple arithmetic operations will eventually transform every positive integer into one. The example on the Wikipedia page shows the two operations is, let's say we have a number. If it's even, we're going to divide by 2. If it is odd, we will triple it and add 1. So we're going to do 3 different approaches, and the first is the simplest. It is the least efficient, but it gets through a few key elements of coding in Maple. So we will begin. We're going to go from 1 to 10,000. We're going to look at all those values and see if the conjecture is satisfied by all the numbers. So I'm going to report a vector which is going to count the number of operations that we do listed here. This is one operation before we stop and we get to 1. So again, what is the operation? Well, it takes in a number. This is a user-defined function. It takes in a number. If the number is 1, we stop at we equal 1. This is just to make sure that we don't continuously get caught in a loop. But if n mod 2 equals 0, that means if it is an even number, then we will return n divided by 2, which will be an even positive number. Otherwise, we will return 3 times n plus 1, triple it, and add 1. So we're going to test the numbers, and that's our first programming aspect. And this is a for loop. And in the syntax of Maple, a for loop is written as for the variable that we're looping from the beginning value, although if it defaults to 1, to the final value. So n is going to be our value that we're going to be testing from n loop, but we don't want to change n loop, so this is just the counter of it. N time is the number of times the function, the operation is applied. Okay, so here's another loop. Our loop is to count the number of times calculated, and we're going to limit it to 1,000 tests. We don't want it to go, let's say if the answer is, the conjecture is false, we don't want it to loop to infinity. So what do we do? Okay, n is not 1, then we apply the operation. And then we say we're going to increase the count of how many operations we did for this particular number. We eventually supposedly finish, and then we get a stopping time for this particular loop value, and that's what we record. Once we record it, we can plot on the plot the positive number that we looked at, and the stopping time. The stopping time is, again, how many iterations occurred. If you go to the Wikipedia page, you will see a picture very much like this one. Approach number 2 is very similar to the approach number 1, but it says, wait, if we've already gotten our number back to a number we've already tested, we should just stop and not continually repeat it. So in this example, we're going to actually do 10,000 because it's more efficient. We're still going to have the stopping vector. We're going to still have our function, which again tests if n is even, n divided by 2, otherwise 3n plus 1. Okay, so again, we're going to loop through all the values. Okay, and again, for a particular number, as long as it's not 1, and as long as we haven't timed out, we're going to keep applying this operation. So now this is where we add the if statement. And the if statement basically says is, what if we reduced our number n to something we have already tested? Well, there's no point in continuing to run the system because we know it works. So what is our time, or the number of operations we need in order to get this to work? Well, it is the time we've already counted up plus the time of what we know that we've reduced it to. And then, of course, we can say, hey, we're done. We've got back to 1, and we can stop the whole loop. And that's why we put it there. So if we do that, the problem is then we have 10,000 data points. If we put 10,000 data points, the plot gets huge and it gets lots of red. So what I've done is I've reduced this to 2,000 data points. So I'm basically using 1 out of every 5 points. And this is what that stopping time versus positive integer looks like. Oh, did I say 10,000? I'm sorry, this is 100,000. Now we reach the most efficient way we can do it. We're going to compile some code here. This is probably more than one ever needs to do, but again, we're trying to find the most efficient way. So all numbers have to be, all integers and floating point values have to be passed either as byte size 4 or byte size 8, and all vectors are going to be passed by address, and the data type of that vector should be included. The $sign says don't pass any more information. If you get passed more information, declare an error. So our variables that we go through have to be declared internally as local variables. And here we have listed them and made sure we said : this is what their type is. The loop is exactly the same. We're going to loop and loop from 1 to n. And notice I've reduced. Okay. And we are playing the same game. Inside, here's our while loop, the same as before. But now, instead of calling the user function, we'll apply the user function directly inside. We know one is never tested, so we don't have to test for that. And all we need is these 2 lines. Again, we increment our time counter, and we find that if we have reached a number that has already been tested, then we can increment our time counter by the stopping time of the previous number and set the previous number back to 1 and say we can quit. The key here is this is written at such a basic level that I can compile it, and that makes a huge difference. So instead of using 100,000, we're going to, or 10 to the 5th, we're going to look at 10 to the 7th. And when we use 10 to the 7th, and I want to make sure that we have a max, we time out. We can't go beyond that timeout. That we are basically also passing it the vector, which is a vector of 10 to the 7th data points of type integer form. And we are going to use the code tools usage on our procedure, passing it the information, and the code, all the information will be recorded into the array stopping time. When you do this on my computer with 10 to the 7th, 10 million data points, it took about 90 seconds to go through 10 data points. But that's the uncompiled version. Okay? I don't know why I wrote 82. Sometimes it was 18, sometimes it was. When I did it with the compiled version, so calc stopping time C, it took a second. So it is between 80 and 90 times faster by compiling. And the plot looks exactly the same, but now, of course, we're plotting not from 0 to 10,000 or 0 to 100,000. We're plotting from 0 to 10 million. And at 1 second, you could easily go to 100 million or a billion. So if you made it through all of that, you'll see that, again, we started with something fairly simple with a few programming type operations, a couple loops, for do loop and a while do loop, and a conditional statement through a function. And we eventually ended up with probably the most complex way of writing the most efficient Maple code. If you're interested in looking at another example, I did an example involving Monte Carlo approximation to calculating an integral of a surface area, and that's linked here in the video.